In this video, we'll see how to incorporate a Class D amplifier IC for audio applications. The board you're seeing here features a Texas Instruments 2-channel, 15 watts per channel Class D amplifier that is fed by 2 audio inputs and connects to 2 speaker audio outputs. We'll go through the basics of the schematic, PCB design, looking at the datasheet, and then also looking at some examples using this board, for example, for guitar applications. A huge thank you to PCBWay for sponsoring this video. I had these Class D demo PCBs manufactured and assembled by PCBWay. I'd strongly suggest checking out their services if you haven't already, and I'll leave a link to them in the description below. If you'd like to get these boards manufactured for yourself, or if you'd like to follow along with the reference design, I have uploaded this to my GitHub repo, and I'll leave a link to this in the description below. You can look at the design and manufacturing files and also order with PCBWay. Make sure also to follow them on Instagram. Occasionally you'll see some posts also from me and some boards that will come up in future videos. Although we won't go into much detail on Class D amplifiers and how they work, there are many resources available online and in books, we do need to understand the basic operation of a Class D amplifier for us to design a schematic and a PCB for this, to see where are the critical elements, what components might we have to size and choose, and so on. I'd strongly suggest checking out, for example, this video by Afrotech Mods, which I'm sure you're familiar with, which is a Class D amplifier tutorial which goes in great depth. In this video, we will look more of the hardware design aspects. With these types of amplifiers, we are predominantly looking at audio applications. When we're going, for example, from a low-level, line-level signal, an input signal, this might come a CD player or your computer audio output, and we want to drive, for example, speakers of considerable size on the right-hand side. Somehow we have to convert our input signal, which is low level, low energy, into a fairly high power, high energy signal that can drive these speakers. Amplifiers for audio exist in many different wattages, so power ratings anywhere down to a couple hundred milliwatts to several kilowatts. Class D amplifiers are especially useful because they provide a very high efficiency, theoretically up to 100%, but of course in practice it'll be lower than 100% efficiency. If you compare that to other amplifier classes, for example the worst efficiency being Class A, you're getting very, very low efficiency, you're getting a lot of power wasted compared to how much power you're actually delivering to your load, to your speaker. Again, I'll leave links in the description below, but I'd strongly suggest checking out this Wikipedia page on power amplifier classes and showing you why some classes are different to each other, what their operating principles are, and also their efficiencies. We will look at Class D amplifiers because they're very, very common these days. You will often find them in digital audio equipment. You will find them, for example, in your car audio systems, and because they are very, very efficient. A downside, especially in the audiophile community, why people might disregard Class D amplifiers is because they are fundamentally switching amplifiers. Switching amplifiers can introduce unwanted harmonics, they can introduce distortion, noise, and so on, and of course that might not be a good thing in audio. However, these days modern Class D amplifiers are very, very respectable with low THD, low noise values, so they can be a sensible choice in many applications. The basic operating principles of a Class D amplifier are as follows. We take, for example, a sinusoidal input. This might be our line level audio signal, which you want to amplify to drive a speaker. So we start on the left-hand side and we feed our line level audio signal, our AC signal, into a comparator, which compares our input signal to a triangular wave generator. You probably will have seen this construction before, and what we get at the output of our comparator is a PWM signal, so a pulse width modulated signal, which is effectively an encoded version, very simply speaking, of our input sine wave modulated by a triangular wave. Depending, of course, on the frequency of the input or the signal parent of the input, the output signal, PWM signal, will change, for example, its duty cycle. However, the fundamental switching frequency is set by this triangular wave generator. Then the actual amplification stage happens in this switching controller and output stage. We have a transistor gate driver, which drives our output stage, which is typically a complementary pair of FETs, very, very simply speaking. This then takes this PWM input signal we had after the comparator output and maps that, or amplifies that, to the supply rails of our Class D amplifier, and we get this very large output swing waveform, which is pretty much identical except for amplitude to the output of the comparator. Now you might think, very rightfully so, that this isn't particularly useful other than that we've scaled the amplitude by quite a large amount. We now have a very, so to speak, harsh sounding output waveform, this square wave output waveform. We want to reconstruct that to give the amplified version of our AC, let's say, sine wave input signal. The way we do that is by utilizing a low pass filter. We wouldn't want to use an RC low-pass filter because, of course, you want to drive a speaker which might have a very low impedance, so 4, 8, or 16 ohms. We also don't want any losses in our low-pass filter. Therefore, we use an LC, so an inductor and capacitor low-pass filter, which forms a second-order output low-pass filter, which attenuates high-frequency harmonics apparent in this PWM amplified waveform, thus hopefully leaving us on the right-hand side an amplified version of our input sine wave, which we can then feed to the speaker with considerably higher power than what our input signal had. And that's the basic operating principle of a Class D amplifier. Now, we won't be designing a Class D amplifier from scratch, although that is a pretty cool exercise to do and would make probably for a very good future video. We are going to use an off-the-shelf Class D audio amplifier IC and see what external components we need and how we can integrate that into the design. In general, this is the approach I would recommend unless you have a very, very specific application. Pre-designed, so to speak, Class D amplifiers will typically be in far superior performance, power efficiency, and ease of integration. You can check out your preferred distributor, for example, Mouse or DigiKey, look for audio amplifiers, and you can see many different classes of amplifiers, also output powers ranging all the way from milliwatts up to several hundred watts of power in SMD or through-hole packages. So depending on the application, if you're creating, for example, a 100-watt guitar amplifier or 500-watt audio system, there will be an IC for you. In my particular case, I went with a Texas Instruments part, this TPA3116D2, which is available in many different power ratings, 15 watts, 30 watts, 50 watts, and this is per channel, or you can bridge the channels to give you double that for a mono system. In my case, just because I don't need particularly high power requirements, for example, for my application, which is a guitar amplifier, I just went with the 15 watt version, so 2 times 15 watts left and right channel. You can check out all the specs and you would select your Class D amplifier depending on what output power you want, what your minimum load is, what your power supply voltages are. So there are many different aspects to designing or incorporating a Class D amplifier IC, so make sure you check out all the parameters and scale them to your application. Again, the reason for me choosing the TPA3116 in the 15 watt variant is that I wanted to run it off a 15 volt supply. So in the top of the datasheet, we can see we can run this off a 15 volt supply. I wouldn't need a 24 or 21 volt supply, and it's 15 watts per channel, which is completely fine for most guitar amplifiers. That's already very, very loud, into an 8 ohm load, which is a typical guitar amplifier speaker. This particular IC has many very cool features and it's very, very easy to integrate with, as we'll see. We can select the switching frequency, it is over 90% efficient, it has various protection circuitries, and it's available in pretty easy to solder packages with exposed pads. As we'll see, the schematic, when you're trying to incorporate a Class D amplifier IC into your design, is pretty straightforward. Effectively, we just have to follow the datasheet and make some choices depending on our application. Our inputs are on the left-hand side. We have 2 1/4-inch TS barrel jacks, and this could be from your line level output, so this could be from preamp. At the top J1, we also have the DC power barrel jack, which provides 15 volts and ground as our power input. On the right-hand side, we have the 1/4-inch output jacks. Again, these are TS, so tip and sleeve. And again, I chose these types of jacks because I'm interfacing, in my case, with a guitar cabinet, which take 1/4-inch leads. Then in the center, we have all of our components that make this Class D amplifier IC work and that are suitable for example, in my case, guitar and audio-based system, giving 15 watts per channel. Going over to the datasheet, this is where we find the pin functions and what we need to attach or how we can need to connect each of these pins. What you'll see is that the schematic is very strongly based on the typical application schematic provided on page 26 of this datasheet. Many of the elements we see in the datasheet we will see in the schematic. Starting with the power section, again we start from the DC barrel jack, which provides nominally 15 volts from, for example, an AC-DC wall wart. We have optionally a TVS diode. We could of course add in reverse polarity protection. Keep in mind this is a demonstration board, so very, very simple, very bare bones. Anytime you see a red cross, this is a do not place part, and this is by default not fitted. The 15 volts is supplied pretty much directly to this TPA Class D amplifier IC to the power pins at the top. And of course, they need bypassing and decoupling. The general guideline is 1 small ceramic capacitor, small being around 100 nanofarads per pin, and you'll see that in the datasheet as well. We have 5 pins, and that's why we have 5 of these small, around 220 nanofarad capacitors. The datasheet also, however, recommends large electrolytic capacitors, at least 100 microfarads, and 2 of those in total. And that's why I went with these large 220 microfarad capacitors, and we'll see when we come to the PCB design how these are placed close or further away from these power pins. We also have to take care of also the voltage rating of these capacitors, and this is particularly the case, of course, also for ceramics and class 2 multi-layer ceramic capacitors, because they will derate, so their effective capacitance will drop with applied DC bias. So these capacitors should have around double the DC rating of the expected power. So we have 15 volts here, so we maybe should choose a 25 volt, 35 volt, or 50 volt rated capacitor for these bypass and decoupling capacitors. On the bottom side, of course, we have the ground pins, but this IC also has an exposed thermal pad, which is very, very critical for heat dissipation, and we'll see how to connect that up when we come to PCB design. The audio inputs, again coming from these 1/4-inch input jacks, are fed into the right and left channels of our Class D amplifier IC. The right and left channels of our Class D amplifier IC, as we can see here, are differential, so we have a positive and a negative part per channel. The datasheet states you don't have to use them differentially as inputs, so if you're coming from a differential source, it will of course make sense to continue the differential fashion. We can either convert our single-ended signal to a differential signal using, for example, op-amps, but in this case, also as the datasheet recommends, what we can do is feed the single-ended input simply to the positive part of each channel, and the negative part we simply bypass or decouple with a suitably sized capacitor. In this case, it's 1 microfarad simply to ground. Because the inputs are DC biased at a non-zero voltage, we don't want this voltage to appear at our input jacks, and that's why we have these AC coupling capacitors, which effectively remove this DC offset, but then also, of course, form an RC filter with the input impedance of this Class D amplifier IC. And we'll see later that the input impedance actually depends on the gain, so the amplification level of this Class D amplifier. Then below that, we have GVDD and P-limit. If we look for P-limit in the datasheet, we can see this is the power limit level adjust, and we need to connect a resistor divider between GVDD, that pin we just saw, and ground to set the power limit. If we connect directly to GVDD, we get no power limit, and that's exactly what I've done here, meaning we get the full 15 watts per channel. GVDD needs to be bypassed and decoupled via a small ceramic capacitor. The next pin, pin 8, is this gain SLV pin. Selects the gain, as well as if it's master or slave mode, depending on the pin voltage divider. So we saw from the schematic, we have a voltage divider here, so this will adjust if it's a master mode, and also the gain. To figure out what the resistor divider values need to be, we can go to section 7.3.1, the gain setting in master slave mode. Depending on what mode you want, master or slave, again, if you have maybe more of these devices and are using the synchronization feature, which we aren't in this design, you might want to set one as master and one as slave. In this case, we're just setting it as master. I've set it to a gain of 20 dB, so again, 1 volt input gives 10 volts output, which means we want a 5.6 kilo ohm resistor to ground, and we want to have an open for R2, so placing no resistor to GVDD. And that's exactly what we have here. What you might have already noticed is also the last column of this table tells us about the input impedance of the audio inputs, and this depends on what gain you use. So the lowest gain, 20 dBs, gives you an input impedance of 60 kilo ohms. Because of our AC coupling, the input impedance along with these AC coupling capacitors will determine the low cutoff frequency of our high-pass filter. Therefore, using 1/2 pi RC, we get a corner frequency of about 2.7 Hz. Then we have various other configuration pins. SDZ is the shutdown logic input for the audio amp. You can see I've tied pin 2 directly to pin 3, and pin 3 is the fault Z pin. And as right below, we can see in the datasheet again, the fault Z is an output pin and it's open drain, which means it needs a pull-up resistor to a specific voltage. So when the fault Z pin is high, there's normal operation, and remember there's SDZ pin high, the output's enabled. If the fault Z pin is low, we have a fault condition. This could be over voltage, over temperature, short circuit, and so on. The fault Z pin pulls low, and because we've tied it to the SDZ pin, the outputs are disabled as well. Then we have the mute signal, and that's hopefully fairly apparent what that is. Then we have these AM0 to AM2 and the mod cell pins. It turns out we can change the oscillator frequency of our Class D amplifier, depending on what we select AM2, AM1, and AM0 to be. If we pull all of them to ground, the typical frequency, of course there'll be some tolerance. The mod cell pin, we can pull either high or low, and this will change the modulation scheme. Pulling it low, this means we will use our typical LC reconstruction filter, which we saw near the start of this video, whereas pulling it high, we go to a different modulation scheme. This will achieve a high efficiency, but it will degrade our total harmonic distortion performance. The output stage, we can see here, the main sections are, of course, the output pins, which feeds into our LC reconstruction filter, so in this case for the right output L1 and C16, as well as L2 and C20. You will see output jacks are effectively differential. We actually have 2 output pins for 1 jack, even though it's a mono output. Therefore, we need 2 2 of these LC filters per channel. This amplifier also uses for the FET drivers these bootstrap capacitors, so C15, C19, C23, and C27, and they are to be attached as shown, again taken from the datasheet. After the reconstruction filter, so these LC low-pass filters, the reconstruction filter values are chosen again based on the datasheet. This will depend on, for example, your switching frequency you choose. You want to, of course, have your cutoff frequency far lower than your switching frequency to make sure you attenuate those switching harmonics sufficiently. But also, if we look at the datasheet, look at section 6.3, recommended operating conditions, the output filter will change depending on what minimum load impedance you might see. I'll leave a link to this in the description below, but choosing inductors and components for the Class D amplifier is pretty critical. So there's also some application notes on, for example, proper inductor selection guides. There's a couple inductor properties we have to take into account: impedance versus frequency of the inductor itself, inductance versus DC current, so derating, temperatures, core materials, and so on. We see these structures here, so for example C17, R8 and C18, and this is repeated a further 3 times. These are optional C, RC, EMI snubbers. Now snubbers you would typically place at the switching node, for example pin 29, 27 and so forth, but if you're having EMI problems you can put these components in place, again following the datasheet. I'd recommend leaving these, for example, as do not place at first and only placing them should you have any EMI problems in your design. Then, after this output stage, we simply feed into the 1/4 inch output jacks. The PCB design for this 2-channel amplifier is fairly straightforward. However, there are some aspects you need to take care of course, and this becomes even more true when you get to far higher power Class D amplifiers. This is a 2-layer board, so on the top we have all of the components as well as all of our traces and polygon pores, and the bottom side of this board is dedicated to a solid ground plane. We'll start on the left-hand side for the input jacks, so we have input right and input left. We go to 2D view. What we want to do is take our signals, so our small signal audio signals, use short traces feeding directly into the input pins via our coupling capacitors. Keeping space from other components, we want this away from digital circuitry and so forth as usual, and short traces as we can. Components such as pull-down resistors for mute signals, or for example the gain selects, they can be placed close to the IC of course, but their actual location isn't too critical. After we've looked at the AC input signals, we also have to consider of course our power flow. We come from this DC barrel jack at the top, we have the TVS diode if we want to place it or not, close to our input connector, and we use wide polygon pores, wide enough to handle the current requirements without any ambient temperature rise that feed into IC via our bypass and decoupling capacitors. As usual, I'd strongly recommend checking out an IPC2221 calculator, which lets you calculate the required trace widths given expected currents, copper foil thicknesses, and temperature rises as well as ambient temperatures. However, it pays off to make your traces not incredibly large, but larger than what the calculator specifies, because this will reduce inductance and of course further reduce the DC resistance and improve power delivery. We come from a DC barrel jack, we use a polygon pore which feeds into our bypass and decoupling capacitors into the power pins which are located here, so 32 and 31, as well as the bottom of the IC 19, 18 and 17. So that's why with our polygon pore in red we have to make this little loop to arrive at both sides of this IC. Of course you could go to the bottom layer and you might have a shorter distance, but what I wanted to keep is a solid uninterrupted ground plane on the bottom side of this 2-layer PCB. What's important is these bypass and decoupling capacitors to have the ceramic capacitors, these small packaged ones, close to the IC power pins. For example, the power pin at the top, we have our bypass and decoupling capacitors very close. Same thing for the bottom side, bypass and decoupling capacitors very close. And further away we can place these larger bulk bypass capacitors, these aluminium electrolytic. Especially on these smaller S&D components, I like to use thermal reliefs, which will aid soldering, especially if it's manual assembly. What's also important for power delivery and thermals isn't just our 15-volt connection, but of course our ground. And we touched about our ground being on the bottom layer, this large continuous solid ground plane. But what you might have already spotted in 2D view is that our Class D amplifier IC in the center has this exposed thermal pad, and this should be tied to your ground. I do have a video on my channel talking about thermal PCB design tips. Just to reiterate here, our thermal source is this IC, and the thermals will pretty much occur directly in the center, which will be bonded to our PCB via solder into our thermal pad, and we want to transfer that heat away as quickly and efficiently as possible. And the way we can do that, for example, is using a top ground plane, but also digging down with vias, grounded vias, into our bottom ground plane, which acts as a fairly sizable heatsink. So we want vias directly down, many vias in parallel to reduce inductance, improve the thermal characteristics. But also we don't want to place too many vias in this exposed pad because otherwise we get problems when we apply solder paste and we get problems with solder wicking. So the pattern I usually like to do is keep a tiny bit of space in the center of my exposed pads and place vias scattered around. And this, for this fairly low power IC, is still fairly sufficient for 15 watts, and keep in mind the efficiency of this IC is over 90%. When we're looking at the output section, we need to think of this as a switching supply, very simply speaking. When we're talking about buck regulators or boost converters, switching converters, similar principles apply for our Class D power amplifier. We have our bootstrap capacitors arranged vertically like so, then we have our output inductors, output capacitors, as well as these passive components which are part of the CRC EMI snubber. I've placed the bootstrap capacitors like so vertically because of how the pins are arranged on this Class D amplifier IC package. So pins 30, 29, 30 is the bootstrap, 29 is the switch node output. The bootstrap connection, for example pin 30, doesn't actually carry particularly much current, therefore a sufficiently sized trace, so typically the same width as the pad of the IC, short wide trace directly into the bootstrap capacitor. The switch node, however, for example the switch node 29 or switch node 27, we should think of very similarly as a switch node in a buck converter, meaning we want short connections. We don't want to make our connection as arbitrarily wide because that adds unnecessary capacitance, and we always, of course, want to keep loops small. Keeping loops small means typically placing components sensibly close to the relevant IC and pins. Therefore, for example, for these switch node output pins that feed into the series inductor, I have polygon pore that expands as soon as I get out of the trace. We need to size our polygon pore to be able to handle the maximum expected current without a significant temperature rise. Again, use the IPC 2221 calculator to help you do that, feeding into our bootstrap capacitor and feeding directly into pin 1 of our output inductor. You can see this connection is very, very short. It's wide enough, but not arbitrarily wide. And the same thing is repeated for all of our 4 output inductors and bootstrap capacitors. Again, thinking about loops, placing components close, but not too close. So if I place these components very, very close like so, I would have problems routing out. And also for assembly, testing and debugging, this wouldn't be particularly helpful. Then in line after output capacitor, we place these optional EMI CRC snubbers. And what I like to do is place the pads directly on the output traces or output polygon pores. The output polygon pores, you can see, for example, these yellowish pores here, again, need to be sized so they can handle the current, which might be in the order of a couple amps, depending on the power you're delivering to your load. And these are effectively differential outputs that feed with sufficiently wide traces or polygon pores into the output pins of your jacks. This happens for the output right jack and the output left jack. Again, trying to minimize the length of these traces as well and size them reasonably in terms of their width. This, of course, all depends on your PCB layout, so what kind of connectors you use, how many channels you have, the power of your Class D amplifier, but the principles remain very similar across different PCBs. To do some very simple no-load tests, I'm going to use my QA403 audio analyzer, which was very kindly sent to me by Quantasylum. The reason I said no load is because I don't have an 8 ohm purely resistive load. All I have is that load box and a speaker cabinet, and those have their own frequency responses, nonlinear characteristics, as well as they're not purely resistive. The connections are very simple. I've hooked up my 2-channel 15-watt Class D amplifier to a power supply, 15 volts, and then also to the Quantasylum with one output and a differential input. I'm just going to run this at 96K, set my input attenuator because we're going to be supplying an input voltage that's going to be amplified by a gain of 20 dB, so 10 times. I'm measuring only on the left channel, so I'll turn off the right channel, which is the yellow trace. And then I would just like to do a function generator first of all, so just a sine wave. You can see in the top left, I'm going to turn this up to 1 volt RMS, and we need to increase the resolution of our FFT, which we can do on the left-hand side in the FFT panel. Already from this, we can see a couple of interesting points. Again, we're feeding in a 1 volt RMS sine wave at 1 kilohertz, and we're monitoring the output, at least in the frequency domain. What we can see quite clearly is, of course, our fundamental at 1 kilohertz, and that's going to be amplified by whatever gain we set. And remember, we set our gain to 20 dB. That's why we're getting 20 dBV at our output shown here. Some other artifacts we can see are due to non-linearities in this whole system. So you can see peaks on the bottom right and the bottom left, as well as some 50 Hz mains noise seeping through, which you can see in a peak on the bottom left. All of these peaks will add and appear as distortion. So luckily these distortion artifacts are quite low, but we can actually use this interface to measure the distortion. So I can click to add measurement, And then on the left channel, total harmonic distortion, as well as total harmonic distortion plus noise. And we can also measure things such as the signal to noise ratio, but also the gain. So I'll add all of those measurements and we can see them at the top. So the gain is spot on. It's 20 decibels, exactly what we'd set our IC to do. Our signal to noise ratio is about 90 decibels for this input voltage. And remember, this is no load. Unfortunately, I don't have a resistive load here. In terms of total harmonic distortion, keep in mind this isn't a particularly meaningful measurement without a load. We're getting around 0.02% and similar values for total harmonic distortion plus noise. This is a good indication that the system is working as expected and we're not getting very large harmonic content at the output. Now let's plug a guitar in, and I'm going to be using my computer as a preamp along with this audio interface, plugging into the Class D amplifier board, again powered by 15 volts, and we can measure the wattage. The output of the Class D amplifier plugs into my Auxbox load box, which is a reactive load box, so it's not purely resistive, unfortunately, which then goes on to a speaker. The reason I'm doing it is because otherwise with 10 or 15 watts, it will blow my apartment apart and I need to attenuate the volume. At least it shows that we can achieve these kind of wattages, what's described on the tin, so to speak. So now with quite a lot of attenuation on the load box, just so I don't blast my neighbors, we have the Class D amplifier being fed by the preamp into the cabinet. Delivering about 10 watts of power. Thank you very much for watching this video. I hope it was useful and I hope it showed you how you can incorporate Class D amplifier ICs very easily into your own designs. If you liked the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any new hardware, embedded systems, firmware videos, and more. Thanks again for watching, and I hope to see you in the next video. Bye bye.